10:59. Give Andrew a couple more moments.
Yeah, just kick me out.
You can join the crowd on Zoom today. Share screen.
So Paul and Terry need to go.
Welcome back from the field trips. 460. How did you guys? How's your trip? You get to find a new destination, right?
Yeah.
That's too bad. Yeah. Soils and forestry students were on the North Idaho field trip, so 456. That was a good one. We only fell behind schedule on one of the days and cut a couple stops out, but it was really great. We saw a lot of really cool soils, multiple different soil orders, and we can think of these all the soil pits that we saw on our trip in the context of our soil processes, which was our topic Thursday last week. We got the video up on Canvas, also the slides. I forgot to post the slides last week. Those are now available on Canvas if you're still catching up from last Thursday. But last time we had lecture, we talked about these processes in soil. We have four main processes representing additions, losses, translocations, or just movement in the soil, and then transformations. You actually hear. Components of the soil are converting or transforming into other components, we could say. And why these are important, what do they explain? Specifically, they explain how our soil horizons form. They're the processes, like these mechanisms that create all the soil profiles that we can observe. So continuing the review, I mean, we started out with a little bit of NBA trivia. We had the basketball player up on the slide, nicknamed the process, right? It was Joel Embiid. I'm doubling down a little bit more today on the basketball analogy and continuing. So we can also think of these processes in terms of the NBA and NBA history. So we have additions, when teams are added. The Milwaukee Bucks were originally an expansion team that were added to the league in 1968. It was Las Vegas, potentially the next expansion addition team of the NBA, maybe in the coming years. We also have subtractions. There's been losses through the NBA over time. There were teams like the Pittsburgh Ironmen back in the 1940s, Providence Steamrollers, Kentucky Colonels, this KC logo here for Kentucky Colonels. Translocations, teams have moved around plenty. The Seattle, the Supersonics, very famously moved in 2007, 2008. So there was a translocation and a transformation. They transformed into the Oklahoma City Thunder. What else? Other transformations, translocations. We've got these Chicago Packers that only lasted one season way back in the day, because it's a little ironic to think of a team named the Chicago Packers because of football. We have the Chicago Bears and the Green Bay Packers, who are rivals. Why would Chicago have a team named Packers? Well, because of the meat packing industry, really important in the Midwest back in the day, which is why the Packers are named what they are, for the meat packing. And Chicago had the same deal, but it was very unpopular for the one season that it lasted because the Green Bay Packers were already around. They changed to the Chicago Zephyrs, I believe, after 1 year, and then bounced around many more times, really kind of convoluted, complicated history. Eventually, they became the Washington Bullets, which are now the Washington Wizards. So the Washington Wizards franchise traces back to the Chicago Packers originally. And then the Charlotte Hornets also on there, another case with multiple applying. They were an addition, an expansion team in 1988, translocated to New Orleans. Maybe the 90s, they became the New Orleans Hornets for a little bit. And then there was another addition, expansion team of the Charlotte Bobcats in 2004, I think that was, who then only in 2014, 10 years ago, transformed back into the Charlotte Hornets as we know them today. So, multiple can apply. NBA, soil, maybe not so different after all. And we have these processes in soil explaining how these teams arrive at their current state, but it's really these this other set of topics, the soil forming factors, which explain maybe instead of the franchise itself, more about like the actual roster construction. So we've got these soil forming factors we're going to talk about for the next 4 or 5 lecture topics, working through these soil forming factors, which we can call, we name them CLORPT. CLORPT is our acronym, our nickname for these 5 soil forming factors. We're going to cover the first one today of climate. CL in CLORPT stand for climate. And then going through the letters there, we have organisms, relief, parent material, and time. So these 5 characteristics of any soil profile, rather than explain how these horizons are forming, these factors explain, or they determine what the soil profile looks like. Think about the whole entire monolith collection we have in the soils lab. The reason that all these soils are so different, diverse, so beautiful, such a wonderful collection, is really because of these different soil forming factors. Soil forming factors explain why the soil looks that way, not specifically the how, because that's what the processes are for. So they explain why the soil looks like that, and then it's important to know that all of these 5 factors influence all soils. Whereas before, it was possible maybe to have a soil profile where no additions are happening, something dominated by transformations or translocations or losses or something. Any given soil profile is going to be influenced by all 5 of these factors. It's just the differences arise when certain factors dominate over others. The reason we have these 5 soil forming factors, the first person to characterize them was one of our most famous figures in the field of soil science, a man named Hans Jenny. He was born in Switzerland. He's a Swiss soil scientist. He moved to the US though, and kind of thought about soils, and specifically in the US, by driving around to all these different regions and states and thinking about how the environment is changing and how that influences the soil. In the early 1940s, I think it was 1941, he published The Factors of Soil Formation. And really, it's kind of been a fundamental of our field ever since. There's some discussion of maybe expanding. It's time to expand the 5 soil forming factors, but we'll talk about that closer to November. I think around November, we'll get to some of the discussion about the soil forming factors. But this is where we're starting out, at least. And here he is. That is Hans Jenny with his 5 soil forming factors. If you'll indulge me in continuing our basketball comparison, we can also consider the formation of NBA team rosters similar to the soil forming factors. This is Adam Silver, who's the commissioner of the NBA. But you can think of basketball team construction as having a similar set of 5 factors that all teams use all 5 of these, such as the draft. Every team gets draft picks every year. You can make trades of players and also draft picks as well, signing free agents from other teams. And then there's also the undrafted free agents, the UDFAs, players that don't get drafted that are available to anybody. Perhaps they're not drafted for a reason because they're maybe not quite as talented as the lottery picks, at the top end. But certain teams like the Miami Heat really are well known for scouting these diamonds in the rough, if you will, finding these players that are available to all teams, but they identify the ones that they like and elevate them through their Heat culture, if you will, to starting caliber players. But then also the money, the luxury tax payments, if you will. All teams have the option to extend, sign players to new, higher, more valuable contracts. There is a salary cap in the NBA, so the rich teams don't have this unlimited amount of money to spend on players. That maybe keeps it fair between like the Los Angeles Lakers, the New York Knicks, versus more small market teams that maybe have less money overall. So all teams are restricted to a maximum amount of money that they can pay their players. You can go over that as a team if you have a lot of really expensive players. I'm thinking about like the Golden State Warriors with Steph Curry, Klay Thompson, Draymond Green all at once. They paid a lot of money. They went over the salary cap, so they had to pay extra money to the NBA in the form of this luxury tax for keeping all their really best players. So all teams use all 5 of these factors. It's just the differences arise from whether or not you're a Portland Trailblazers or Charlotte Hornets team that's kind of the bottom tier of the league, getting these high draft picks every year, versus a team like Boston Celtics, the Denver Nuggets, the more recent NBA champions who have elevated their roster through prioritizing certain factors more than others to become, the championship contenders. So all 5 soil forming factors affect all soil profiles, much the same way that these NBA factors affect all teams. It's just the differences arise depending on what is prioritized. So our first one, as we walk through over the next couple of weeks here, we're talking about climate. The most important part of climate as it affects soil formation is the temperature and the precipitation. Moisture is a huge one. The reason that climate is really important to soils is it has a really strong effect on the weathering potential, weathering occurrence at any given soil profile, and also the vegetation that you have on the surface. Vegetation is its own soil forming factor, through organisms, but these two can be really hard to separate sometimes because, moisture availability really
influences what is able to live there.
Yes, influences maybe the plant communities, but also water is really important to our processes. So perhaps it makes sense for us to start talking about precipitation first, and the amount of water. A measure of how much precipitation any soil profile receives, we describe as the mean annual precipitation. So the total amount of water or precipitation received in a soil profile is important, but how much, but it also matters when, in terms of the temporal distribution of this precipitation. Is all the precipitation falling in the winter and the spring, kind of like it does around here with a really dry summer, or is it more evenly distributed throughout the year? That can have an effect on what happens in the soil. All these differences between both the total amount of precipitation and our temporal distribution of it, we describe in, we call them SMRs, a soil moisture regime. We'll cover the moisture regimes in depth a couple weeks from now, but we as soil scientists at least have a organization to a classification system of describing temperature or the temporal distribution of precipitation as well as the total amount. Also important to consider the effective precipitation, so not only how much falls from the sky, but how much of it actually enters the soil profile, would interact with the soil. This would not include any water taken up by plants directly. Water lost through evapotranspiration. This ET here means the water that's respired by plants, or maybe that just runs off the surface. If we're interested in like how water drives these subsoil soil formation processes, it's important to recognize there might be a difference between the total amount of precipitation and the effective precipitation from the subsoil's perspective. So what happens as our mean annual precipitation changes? What can we kind of expect to see as common patterns? Generally, of course, if we're going to kind of broaden this out to all soil profiles in general, as you increase the mean annual precipitation, soil acidity will generally increase. If rainwater is a little bit on the acidic side of neutral, you can increase the soil acidity. Increasing rainfall also increases the depth to calcium carbonate accumulations. That's what this figure here is showing. As rainfall increases from lower on the left side, increasing to 100 centimeters of annual rainfall per year on the right, the depth in inches and centimeters here, going from 0 at the top to 3 meters here at the bottom. It's increasing. It's like a depth of the soil profile. So each dot here represents the depth of calcium carbonates in the profile. And as rainfall increases, as you have wetter and wetter soils, the depth that you observe carbonates is increasing as well. So depth of calcium carbonates. We remember calcification as a process in soils usually happens in the dry areas. Perhaps that makes sense. Areas with less rainfall will have carbonates closer to the surface. Organic matter content is another one. Again, probably closely tied with the biomass production, where you're able to have more plant growth, you're able to incorporate more organic matter over time. Similar to the calcium carbonates, we've got clay illuviation. If you need water in the first place to pick up these clay particles, carry them down through the profile, and eventually form these clay films on the edges, on the outsides of soil aggregates. You need water flowing through the soil pore space. That requires maybe a higher amount of mean annual precipitation. And then weathering. So yeah, here's depth to maximum clay. So as the mean annual precipitation increases as well, again, we have 0 at the top to 100 centimeters at the bottom. With more precipitation, you have more water, you have less sauvage as a soil process, transporting clay to the maximum clay content deeper in the profile. And then also weathering, the amount of mineral interactions. If you are trying to break down maybe hard bedrock into sand, silt, and clay to form soil, it helps to have water to speed that process along. So we have those carbonate and clay illuviation figures there. Okay, let's think more about the temporal effects. So the difference of when the precipitation falls. You don't have to draw these out or anything. We'll think about these quite a bit more. This is kind of a preview of what we're going to get into later. Some of these example soil moisture regimes, if you will, are the xeric, which is what we have here on the Palouse, characterized by a really wet winter and a really dry summer. So if we think of these figures, let's say we have precipitation and evapotranspiration on the same, the vertical scale here, it's going to be the blue symbols are precipitation. So these are months of the year here in their numbers. In the middle of the year, this would be June, July, August. Precipitation is the lowest. These blue triangles are down low here, much higher in January, November, December. And this kind of works as an inverse to this potential evapotranspiration, the red symbols here, when the plant uptake or the demand for water is the highest, we receive the lowest amount in precipitation. This is kind of the opposite of the austic soil moisture regime. So maybe these two figures here, or a soil forming under these two soils forming under these two regimes, maybe receive the same amount of total precipitation per year. It just is distributed through time a little differently. So the austic precipitation distribution could be either more even throughout the year, or this example here receives more precipitation in the summer, right? This is May, June, that gets the most. But this corresponds directly to the plant uptake. So Again, it's a similar total mean annual precipitation, just falling at different times can create some pretty significant differences in the soil profile. What could this look like? Here's two example profiles. One forming under an ustic regime. This is an Ustal soil profile on the top, and a Zerol Palouse example here specifically in a xeric moisture regime. So again, in our ustic regime, plants are able, they're growing during the summer, they take up summer rainfall. The soil stays relatively dry is what that means. So the amount of water that percolates through the profile is a lot lower because the roots kind of intercept it. Soil stays dry, and we observe calcification happening in this kind of 1 meter depth here, even shallower than a meter. This white kind of chalky material here would effervesce. If it's an HCl, we might put a BK horizon on that. We see the calcification, whereas in the xeric profile, all the rain and the snow, our precipitation is happening in the winter, where maybe plants aren't growing quite as productively. There's less demand for water from roots in the soil profile. More water is going to flow through and essentially flush out, wash these carbonates from the profile is what's happening. So at the same 1 meter depth here, we don't have a BK. This is maybe more of a BW horizon. Weakly developed. There's too much moisture for calcification to be occurring. So in this figure here, the percentage, this is calcium carbonate as a percent. Maybe these two profiles have the same total amount of precipitation, but just depending on the distribution, you can see calcium carbonate occurring in the soil profile much shallower in this ustic compared to the xeric soil moisture regime. Moving on to our temperature now. Temperature, of course, a measure of really how hot, how cold does the soil get. We can describe, or for any soil, any location that we're interested in the soil, we can find the mean annual air temperature. This would be like the weather forecast, maybe that I check in the mornings when I wake up. I want to know or maybe the mean daily air temperature rather than annual. So there's perhaps a difference between the mean annual air temperature and the mean annual soil temperature. In this part of the world specifically, it can be harder to, check the local news and get the soil temperature forecast for the day. But the rule of thumb here on the Palouse, at least, is the mean annual soil temperature is going to be 1 degree warmer than the mean annual air temperature. What this means here in Moscow, at least, is that if our mean annual air temperature through the year is about 48 degrees Fahrenheit, our soil temperature will say around 50 degrees Fahrenheit, average through summer and winter. Yes.
How deep into the soil do you store?
That's a great question, because you can expect it to change throughout the year. We're just a couple slides away from that. Good question. More reasons why temperature is important in the first place. Of course, it controls the effective precipitation through the vegetation. What plant communities do you have growing? How do those plants interact with water? What's their demand for water? Also driven by the temperature. Chemical reaction and decomposition rates can be affected by temperature, where you have maybe more microbial activity. Metabolic processes in general happen faster as we increase the temperature. And it's important to recognize that our soil temperature can change both daily and seasonally. Things that affect soil temperature, what goes into creating different temperatures, conditions in a soil profile. I think number one is solar radiation, the amount of sunlight sunlight any given soil receives as a function of the day length, how long is the sun shining on it, what direction is the soil surface itself facing, so the aspect, there's going to be a big difference in incoming solar radiation on the north side of a slope versus the south side, our aspect or direction. And then also the albedo, if you will, or the amount of light that reflects off the surface versus being absorbed. So this could be like the color of the soil. More lightly colored soil is going to reflect light more than dark colored soils will. And we already know, thinking about moist color versus dry color of soil, where a soil profile holds moisture, maybe it's a darker color, and it will absorb more radiation. Also, do you have any cover on the soil surface through vegetation? What kind of canopy coverage is there, if any? And an important consideration for agriculture as well. So are you leaving a cover through like a cover crop or residue, like crop residue on the surface, if you're in maybe a no-till system, that can add a lot of coverage over the soil surface, maybe keep erosion down, but also reduce the amount of incoming sunlight and the soil temperature. So in like really hot areas where
Soil cover also helps the microbes, because some of them are very sensitive.
yes, that could, if you want to increase microbial activity and maybe it's so hot in the soil profile that it's restricting microbial activity, maybe adding cover will promote the soil for microbial habitat or activity. Additionally, with soil cover, something to think about, we have a new grad student in our soils department that has a background in soil consulting, working on a lot of projects where solar farms are being constructed, so like solar panels on the soil surface. And that will add, in addition to like erosion, which probably you talk about the most, imagine rain falling on these impermeable surfaces being concentrated, like rainfall running off of a solar panel, be a lot more concentrated on the maybe each row of panels, but also they're going to shade the soil surface below it. So any covering you have on the soil surface could affect the temperature that reaches the ground level. And then this all, of course, leads to the soil water content, the amount of water in the soil, which we know already affects the soil processes here. Okay, so that's what affects soil temperature from the overall, like the general standpoint. If we're gonna get a little more specific and think about thermal properties of the soil itself, you can think of specific heat of any object. I think back to doing this experiment with like water in my high school science days, but a specific heat is just a measure of how much energy is required to raise the temperature of any substance by 1 degree Celsius. So the specific heat of dry soil, if we're measuring energy in terms of calories or joules, are these two units here. Dry soil can be increased by 1 degree Celsius in temperature with only 0.2 calories per gram of soil, 0.8 joules per gram of soil. I'm not gonna expect you guys to remember this specifically, but this is just a comparison to water itself as a specific heat of 1 calorie per gram of water, or 4.18 joules of energy per gram of water. So that's much higher specific heat. That means water is able to insulate itself against changes in temperature easier than dry soil will. So if you are comparing a dry soil to soil that contains a higher moisture content, it's going to take a lot more energy to increase temperature in systems that contain more water. So not only would you have specific heat, which is heating up soil in the first place, we also have the thermal conductivity as a kind of physical property of soil related to the temperature. Conductivity is a measure of the transfer of heat through the profile. So where you have the soil surface receiving all of this solar radiation, the sunlight, increasing the temperature, how does that heat move down through the profile, raising or lowering temperature of the subsoil? And what this does, this conductivity through soil, can create lags in the mean annual soil temperature over time, where the surface of the profile maybe is really hot in the spring and the summer because it's getting the most sunlight then. It still feels like winter in the subsoil because the heat is being conducted downwards at a slower rate. So the heat's moving, it's getting there, just a little slowly. So now we're going to get into what Andrew mentioned, fluctuation in temperature. How do you decide, or how do you take like a single daily measurement and decide what the soil temperature is? What's representative here? Well, if you start by measuring a single soil profile on a summer day, perhaps under a live oak tree, so maybe in a little shaded spot, we have on this figure temperature on the left, the time of day from midnight to midnight, and each line here is, imagine like a thermometer or a temperature probe at a different depth of the soil profile. So the dark blue line here is right at the surface. It's coldest right in the morning, maybe where sunrise takes place, and then temperature increases gradually throughout the day. By mid-afternoon, late afternoon, it's the highest temperature. This is pretty relatable, pretty intuitive, I think, as we look at daily air temperature forecasts. But as we go down to the soil profile, it really kind of evens out. So just 10 centimeters deeper, we see the lowest temperature of the day happens probably a couple hours after we reach low temperature at the surface. High temperature, just 10 centimeters down this pink line, happens again after that peak. We've got a lag in the temperature response. But then by the time you get 35 centimeters down, 1 foot, this yellow line here, if you can see it, it's really flattening out here. And then 50 and 75 are these two, the light blue, purple line. Those are really kind of steady throughout the day. Not much daily variation. So there, we do see great variation at the surface here, but it mostly stops by the 35 centimeter depth in this example profile. And on a summer day here, we observe cooler temperatures deeper into the profile. Since we know about thermal properties, specific heat and all, I would imagine there's a much greater variation in relatively drier soil profiles with a less energy intensive requirement to change the temperature versus a soil profile with more moisture in it. Maybe these lines would across the board be even flatter. But this rule of surface being warmer than the subsoil, is the subsoil always going to be cooler than the surface? Perhaps not. Yes, this is the summer example. If we look at a daily fluctuation through the winter now, we see really the same kind of characteristics here. It's very variable at the surface, but now the warmer temperatures are found deeper in the profile. It gets coldest once again in the morning, warmest in the afternoon at the surface, but compared to each of these measurements deeper in the profile, it gets warmer deeper in the profile. Yes.
I have a really dumb question, but just tell me. Okay, so we're talking range, right? Like, are you gonna see a difference in, say, a prairie dog town and like a regular, just non-disturbed area? And like, what is that temperature change gonna look like?
What would temperature change look like in an area with a lot of like biological animal activity?
Right,
Because you can imagine these prairie dogs, like they're burrowing. There's
right,
more air in the soil profile. Air has the lowest specific heat of any of these things, right? So I would think, I don't think I've ever thought about that before, where you have essentially these huge macro pores in the soil, uh, exchange of air. Uh, I would think that makes the daily fluctuations a lot greater. So if the air is mixing, I suppose maybe it's really well insulated. I mean, the reason that prairie dogs would burrow in the summer is because it's cooler in the soil, right? So I definitely think that would increase the mixing, the conductivity, if you will, if you add a lot of air to the system. Not a dumb question by any means. So that's good. Thank you, Daisy. Okay, so these are the daily fluctuations, right? If you can imagine, how do we compare like the summer and the winter together? What if instead of a daily figure here, we plotted, or no, I'm ahead of myself a little bit. So let's see, these are two specific examples. In general, though, what do we see here? Most soil profiles, coldest in the morning, warmest in the evening, right? But we reach a relatively constant temperature at a 50 centimeter depth. So you can imagine these figures, the schematic graph of a diurnal, a daily soil temperature variation with depth. It would kind of wave back and forth. It would swing where right here at the bottom would be 50 centimeters deep, relatively constant, but then by, let's see, yeah, at sunrise here at 6 o'clock, it's the coldest at the surface and increasing as you go down. But then this is going to lead the way. By 9 o'clock, it's the surface is warming up, but then subsoil, this is maybe 10, 20 centimeters down. It's still cold, it's catching up. And then by the time it's mid-afternoon, sunset, the soil is starting to cool down here. Or noon, it's all the way there. And then by the time it's starting to cool around sunset, surface is reacting a lot faster, and then this is kind of catching up. So it kind of wave back and forth like this. By 50 centimeters deep, you reach the same kind of daily temperature. Now, what does that look like over the year? It's really kind of similar, where as the months go by, you have the same kind of action like this, except imagine my fingers being the daily scale, they would be doing their own waving up here, still going back and forth, where maybe it's warmest in coldest in the middle of the winter, January. Here's this green line where the soil profile going down all the way, this is 3 meters here, is at its coldest. And then as the spring starts to warm up, the surface reacts faster. And then all the way through the summer where it's warmest throughout. Temperature changes fastest at the surface, heat slowly conducts down, happening on the annual scale as well as the daily scale, right? Similar pattern to daily fluctuations. And just like we saw in the last figures where the maximum daily soil temperature was like 6 o'clock, 7 o'clock, kind of early evening hours, compared to maximum daily air temperature is like 3 or 5 p.m. There's a lag there. There's also a lag here where the maximum temperature might occur in September, where the soil has been gaining heat. It's been receiving the solar radiation. Temperature has been increasing all summer long. Only now it's starting to cool down. Check the weather forecast here in Moscow, definitely starting to cool down from where we were in the summer. The soil is it's retaining that heat. The surface is starting to swing back, but maybe the subsoil is still at its maximum temperature extent. Okay, so with about 10 minutes to go here, this is enough theory behind soil science, but I like looking at pictures. What do these climate effects actually look like in the soil? If we were going to compare temperature, so let's find 2 different soil profiles with a similar mean annual precipitation. So let's hold water the same and just compare different temperature regimes. We've got a New Mexico soil profile, annual temperature 54 degrees compared to North Dakota. with 42 degrees average annual temperature. What do we see here? I mean, it's a lot deeper A horizon. There's a lot more topsoil in North Dakota than New Mexico, or more carbon rich at least. So we can say that in New Mexico with really hot temperatures, it's going to be limited on the amount of plant growth, the accumulation of organic matter. This A horizon depth, is the clear evidence of that. And if we're going to put a process on this, it would be our melanization process. A bunch of kind of individual, smaller scale processes all tied together, creating these dark, deep mineral A horizons. So melanization is going to be limited in New Mexico compared to North Dakota, just because of the temperature. But if we notice in the profile, you have to take my word for it, I guess, because we can't add any HCl ourselves. But both of these profiles have the carbonates and the calcification happening as a process because they're both relatively dry. So that's our comparison of temperature. Now, if we're going to pick two places with similar temperature through the year but different precipitation, we could look at Colorado and Iowa with a similar temperature but different precipitation amounts. And really the main difference here that I see is the higher precipitation in Iowa, like double the rainfall, is really limiting the calcification compared to our location in eastern Colorado. So they arguably have similar melanization. This is just a dry soil profile, so if you can imagine a little more moisture in there, maybe the A horizon would reach down to a similar depth, or at least a lot more similar than our last example was, but similar melanization. The calcification is a big difference. This is like all calcium carbonates here. It'd be a really violent fizzy reaction. With this one, probably not. It's a lot, there's too much rain. The moisture is too high for calcification as a process. So this is an easy comparison to think about, I suppose. It's if you want to understand the effect of climate on soils, you just find two soil profiles with different climates. We could put a fancy name on that. We could call it a climo sequence. Really just a comparison of sites across different climates. For each one of the soil forming factors that we talk about, I'll give you the fancy word for a comparison of profiles under different conditions in those soil forming factors. So this one is a climo sequence. And as far as these sequences or comparisons, kind of structures of soil comparison goes, climo sequences can be relatively difficult to set up, specifically focusing on climate without changing too much about the vegetation or the organism activity along the way. So these climo sequences can be kind of hard to identify. Really kind of the best one that we have to work with, or at least a classic example of a climo sequence, is a study that was done, classic study right back in the day across rangelands in Montana, where we keep, relatively speaking, all the other soil forming factors constant. The only difference across this landscape gradient, if you will, is the amount of rainfall. So in general, what we see here, as the moisture is increasing, so does the plant productivity. Moisture gradient here on this figure goes from dry on the left to moist on the right. Here's a picture, think about what the dry environment is compared to the more, this landscape that gets more rain. We have a deeper A horizon. That's this thickness of the molic epipedon, fancy way of describing A horizon depth. Depth of calcium carbonates, as we saw in the other example, is going to increase as you increase the moisture, but then annual productivity, so the amount of plant biomass, plant activity is much higher in environments with more water, 500 kilograms per hectare compared to 1,500 kilograms biomass. And I think that's not too hard to imagine that in an environment with more water, plants are going to be happier on average. And then adding our soil processes in with the calcification, with this melanization, that's going to create a different soil profile. And climate is what we have to thank for it. So I think that's all I have for our climate slides. Yes, Stacey.
Okay, so kind of going back to so like another quick comparison. Say you're at a pasture that is like straight grandma sod, and right next to the grandma sod is maybe a bunch grass, but they're both receiving about like similar, like they're obviously in the same location, so like
How different can the climate be?
How's that gonna like? How's that changing? Where's that difference? Like, is the bunch grass gonna be cooler because the roots go deeper compared to the sod, even though like they're in the same like similar locations or similar precip, or what's that gonna look like?
So we have two different plant types that have different interactions with water, right? One, you associate one more with more moisture than the other. I think that this could be a difference of some other soil characteristic, like the texture maybe, that because soils have their own ability to like retain water. And do you guys know Georgia Harrison at all? Did you take like botany?
Yeah.
She's the one that taught me like what makes a soil a good versus bad soil for rangeland. And her answer is the moisture holding capacity. So any soil that's able to retain its own water, maybe given not much water to begin with, depending on the soil climate, right? Any soil that's, because of its texture, because of its structure, or any other inherent like physical properties of the soil, is going to retain more water. Maybe that could be just one of the differences. But that's a great question. I mean, and we'll think about this in lab a little bit, but it also speaks to how hard it is to compare like soil profiles with different climates without changing too much about it, because any one place you're looking at a soil profile probably are going to have the same amount of rainfall through the year. So really gradual change. Great question. Anything else before we go? Otherwise, that'll do it for us.